Okay, right now we are going to talk about the feasibility of this free body diagram, where we have our system that is experiencing a force of tension to the left, a force of tension to the right, and then a pull down, a force of gravity down, or if we're saying this is a junction, it could be a force of tension downwards. But the feasibility of this, where our sum of our force acting on the entire system is 0 newtons. The system is not accelerating. In fact, the system is completely static. It is not moving. We need to discuss the feasibility and whether this is even possible for us to experiencing this type of free body diagram where our sum of the force acting on the total system is 0. Now we're going to do that using a big example in the field of volcanology, the study of volcanoes. Volcanologists need a lava sample from an active lava pool below a plateau inside the volcano. After one end of a rope is anchored to the rock, another scientist hikes around the plateau rim so that the rope and an attached cable hangs over the lava pool. The cable is dipped into the lava pool, and then the lava that congeals on the cable is retrieved. So we have our diagram underneath, showing more or less what this is going to look like. Where we have our cable right here, this is where the lava will congeal on. It is attached right here to this rope that goes over to this anchored end, and then over here to where this other person had attached the rope after hiking around. Now we're saying that the angle that forms between the rope and some horizontal plane is going to be 35 degrees. And we're also going to make another assumption that this cable was hung directly in the middle of this rope, so that way these two angles can be equivalent. Now for the actual problem we'll be solving. When the cable with the lava sample has a weight of 125 newtons, how large is the tension in the rope? Now the hint we have here is to make our force diagram for the junction of the cable and the rope. And we do not need to worry about the fact that the rope has weight too. That would just make our force diagram a little too complicated. So I removed all of the unnecessary information. So this way, this is just that same image that we were working with. We have our junction right here. We have our cable, and we have our rope. Now, I ended up just redrawing that off to the side, just to make this a little bit easier for us to look at. I also made sure that those angles made sense. This is actually what a 35-degree angle would look like on both sides. And then, even though this is not really how lava would congeal on the cable, it just allows us to visualize this in ways that we've seen before. So now that I have this here, we have drawn our system and our surroundings in a way that makes it easy for us to interpret. We can identify our system, which in this case is going to be the junction. We shrink that down to a single dot, even though it already was essentially, but we place it out to the side so we don't have to draw it directly over our picture. Then we start to add our forces. The first force that I'm going to draw there is the force of tension acting on the junction by the cable, which has a magnitude of 125 newtons. Now, typically, I say that our first force we draw should be the force of gravity. And this is actually what the force of gravity, or the weight is, of the cable and its lava that was congealed on it. However, our hint was to make a force diagram just for the junction, which that junction is where the cable meets the rope. And we're saying that this area right here was massless. That means that it does not have any weight. But what it does have is it has a force of tension pulling down on this thing. And because this is going to be a static system where the weight is just hanging here, the weight pulling down is equivalent to the tension pulling up, which is why I can say the force of tension on the junction by the cable is 125 newtons. Now, I also have two other forces of tension. Both of them are acting on the junction by the rope. I'm having them match the same angle that I did before, 35 degrees. pointing left and pointing right. Then I break them up into their components because, well, it wasn't really easy for us to explain from this free body diagram why the junction overall would be static. So if I drop it down to this, I say each of those two forces of tension have a horizontal component and a vertical component. We could do force tension X and force tension Y if we prefer, but I'm just focusing on horizontal and vertical here. Now I have already taken my triangle where I have the vertical component here and shifted it over, just to kind of show what's going on here. And something else that I can say is the fact that this junction is not accelerating left or right means that the force tension horizontals need to balance each other out. So that way there's no acceleration left or right. I can also show that with the summation equation here. Sum of the force X is equal to 0 newtons, which means that that force tension 1 horizontal and that force tension 2 horizontal need to be equivalent. Now, I'm going to just be showing this. It doesn't really matter which way we put it as long as we're consistent with this. If I say that left is going to be my positive direction, that means that will be my force tension 1 dash horizontal minus the other force tension, which would be force tension 2 horizontal. Then for my sum of my forces in the y direction, in order for this overall to have 0 acceleration, we need to make sure that overall the forces are balanced. So sum of all the forces vertically are 0 newtons. I have two of those components of tension pointing upwards. So Ft1, y, plus Ft2, y. That adds up to all of the forces pointing upwards. And we take away all of the forces pointing in the opposite direction, that force tension on the junction by the cable. So when we sum up these two forces and this one, overall they should be balanced. Now to actually solve for the force tension in the junction, we need to take the value we know and try to figure out something else from it. So in this case, I'm taking my summation equation from up above. For my sum of my forces, y. 0 newtons is equal to my force tension 1 dash y and force tension 2 dash y. The fact that they have the same angle means that these two would be the same magnitude for the vertical components. That's why it's plus 2 times force tension vertical, plus the minus force tension at the junction by the cable, which is pulling down. I can rearrange that to show that my force tension junction cable is equal to 2 of those vertical components of tension from the rope. Plug in my numbers, and I can say that my vertical component of tension from the rope is 62.5 newtons. Then I can just use simple trig functions in order to figure out how much tension there is in the rope itself. This would be my hypotenuse. This right here is my 35-degree angle, and this right here would be my vertical component, which would actually be over here in the triangle. So the fact that I know the angle and the length of the opposite side to that angle, and I'm looking for the hypotenuse, means I would choose sine. Sine of an angle is equal to the length of the opposite side over the length of the hypotenuse. So I've already plugged in 35 degrees for my angle and 62.5 newtons for the length of my opposite side. The thing I'm solving for is my hypotenuse, which in this case is the force of tension in the junction by the rope. I can rearrange that and solve to say that the force tension in the rope is going to be 108.97 newtons. But this doesn't really answer that original question. Is it possible for us to have a perfectly level rope where there's no sag whatsoever in the rope? To answer that, we're going to take this same volcano problem and try it again, but with a different angle. Because the actual apparatus has a pulley in the middle of the rope. The cable parallels one side of the rope, goes over the pulley and down to the lava pool. The reason is that simply tightening the rope cannot lift the lava sample out. Here is why. Calculate how much tension would be needed in the rope to decrease the angle to 5 degrees. The pulley helps us to mitigate and reduce the amount of force that the human needs to apply. But if we just have the rope, let's calculate what we would need for the 5 degrees. So once again, we're going to draw our system boundary. I'm just using that same free body diagram from before. If we wanted to make this a little bit more accurate, or a lot more accurate rather, we would take my two force tensions from before and actually decrease the angle to match this 5-degree one. And that would make it a much better free body diagram. However, for the purposes of this problem, I'm just leaving it the exact same because we still have the same forces in the same directions where we have the same summation equation. Not only do we have the same summation equation, but the weight of the cable and its lava has not changed, which means the force tension on the junction by the cable is still the same amount, which means that we still need the same amount of vertical tension from the rope in order to balance out that pull down. So we still need 62.5 newtons as Ft vertical on junction by the rope. We can still use that same sine function. However, instead of using sine of 35, it's sine of 5 degrees. That means that when we reduced our angle, we already got up to 717.11 newtons, way more than the 108.97 newtons. The lower and lower and lower the angle gets, the more and more and more force of tension in the rope there needs to be. If we go back to that original problem, where we have a completely flat or 0-degree angle for our force tensions, there would be absolutely no component of the force tensions in this free body diagram that would allow us to balance out the force of gravity. What this means is it is completely impossible for us to have a situation where the sum of our force acting on our system is 0 newtons, where there is a completely static situation, no acceleration whatsoever, no motion whatsoever. An object cannot be hanging from a rope, where that rope, that cable, that cord, or whatever, is completely flat. There will always be some amount of sag because we need some amount of force tension Y in order to balance out that force gravity.